des polycarbonates. Oui, pourquoi pas.
Identification is completed.
Okay, welcome to CERN. This is, in fact, the control room for the ATLAS experiment. ATLAS is one of the 4 large experiments now going on at the LHC, the Large Hadron Collider. The Large Hadron Collider is a huge ring of 27 kilometers, and that's an accelerator where we accelerate protons in 2 different directions, and then they collide in 4 points. We are just above one of those colliding points at the ATLAS experiment. So ATLAS is both a large collaboration of about 3,000 people. I'm one of them. My name is Pauline Gagnon. I'm Canadian. I work for an American institute, Indiana University, and I live here in France and work in Switzerland. But that's just about the kind of sociology that you have with the people here at CERN. So it's a very mixed background. On ATLAS alone, we have people from more than 70 different countries. There are only 38 countries participating in the experiment, but since people like me, I'm Canadian and I work for an American institute, so then there are people from different countries working together. The common language to work is broken English, so everybody speaks it with its own, their own mistakes and all that, their own accent and all that. So, but people get along and we usually get the work done. All this, you may wonder, what's the purpose of all this? Why do we go to such an extent, so much work? 3,000 people just to build the detector and work on it and analyze the data that comes out of it. Essentially, it's just to increase the knowledge about what matter is made of, what is the universe where we live, what is this place we are in, and where did it come from? Where is it going? So it's a very fundamental question. It's nothing that puts food in your plate right away. The food might come later on, because with research, you never know what will come out of it. No, we're going out and let's see what we find. It's a bit like a mushroom hunt, You can bring back something that is really good and you'll make a good dish, or you might not come back with anything suitable. So I was saying earlier that we have the accelerator, which accelerates the particles, and then we have the detectors that are there just to detect what comes up. A detector is just a very fancy camera. So we take a snapshot of what happens when two protons come into collisions. All the energy released in the collision then is in one small tiny point, and it allows you to create a particle because E equals mc squared. So the energy that you have put there, you can transform it into mass. The c squared is just the exchange rate between energy and mass. So we can create new particles and study how they behave.
I saw in 1995 there was an opening at CERN, and LHC was due to start very soon. And so this is why I decided, well, it could be a good opportunity, and that's why I jumped. And so I think it's actually beautiful to be a part of a modern cathedrals building. That's the way I see it. It's like being a community with a single aim and a single scope. And we are producing machines that actually nobody has built before, like a cathedral. I'm in charge of the magnets at CERN, everything that has to do with magnets for the machines. And I arrived at CERN in 1995, after a few years working for thermonuclear fusion. And I think I was lured here by the adventure of the LHC, so it was at the beginning of the LHC. And in fact, where we are today is the hall where we do all the maintenance, the work, the construction and reconstruction of the LHC magnets. We do mostly dipoles here, and we work on quadruples as well. So these are the main elements that make up the superconducting cryostat of the LHC. Well, magnets are the main mass in an accelerator. As you've seen accelerators at CERN, magnets guide particles. They drive them around on a circular path so that they can go back to the real accelerating component, which is a cavity. But they need to do that thousands of times and tens of thousands of times per second, like in the LHC. So the main function of the magnet is to guide the particles back. So this is what we call dipoles, and they have to focus them onto the closed orbit of the machine, and this is the quadruples. In addition to that, the quadruples, they also squeeze the beam down to the small size, like smaller than a hair, in the experimental region. This is the main function of the magnets. To give you an idea of the powers and strength, I think let's start with the electrical power that we're using. because we need electrical power to run the machines. So CERN is using roughly 160 megawatts of electrical power to run all these accelerators. And that's more or less the consumption of a small city like Geneva. So it requires indeed a lot of power, in spite of the fact that we're using superconductors. So the LHC by itself uses about 60 megawatts, and the whole complex before the pre-injectors use also about 60 megawatts to inject the beam into the LHC. As to the magnetic field, to give you a feeling for how strong the magnetic field is, you should imagine a magnetic field in our magnets of 8 Tesla produces forces. And these magnets are 15 meters long, and the forces that you produce on the magnet are of the order of 350 tons per half magnet. So 350 tons per meter of magnet for every half of the magnet. So it's a lot of weight that needs to be taken by the very strong structures that we put around them. This is why the magnets are all encircled in this very strong structural steel that is keeping them together. As to the magnetic field itself, so the field nominal is 8 Tesla. You can compare that to the magnetic field of the Earth, which you can barely see with a magnetic needle. So the Earth is producing here in Geneva about half a Gauss. And if I compare that to the magnetic field of the LHC, which is 8 Tesla, that's a factor of 100,000 more. So we're producing in the LHC 100,000 more magnetic field than we do compared to the magnetic field of the Earth.
We are at 90 meters underground between the Jura and the Lake of Geneva, and this is the cavern of the Atlas experiment. It's the biggest experiment in high-energy physics we ever built. So it's the cavern is huge. It's 60 meters by 30 meters cavern, and inside there is a detector that is 7,000 tons. It's the same weight of the Tour Eiffel in Paris. and the cavern is fully occupied, in fact, by our detector. And this is one of the detectors that has measured the Higgs boson this year and last year. And now we are in maintenance mode, so this is a period in which we stop, we open the detector, and we work on it. So the aim of all this is quite varied. So one of the main aim that is the one that you can find on the press is the discovery of the Higgs boson. That is, apart from being a particle, is a mechanism, is a field, and is the mechanism that gives the mass to all the other particles. But this is only one of the aims of this detector. This is a general purpose detector and can measure several aspects of the nature, and the several aspects of the nature in these very tiny dimensions. And this very back in time. The accelerator itself is a time machine. And going up with energy allows us to go back in time and to reach just a tiny amount of time after the Big Bang. The description of the nature as we know today is at the moment, I would say, quite complete, especially after the discovery of the Higgs bosons. But there are many things we don't understand that for which this detector has been built for. And this, for example, is questions about dark matter. And well, there is one very basic question, that is the difference between the amount of matter and antimatter. Because all this knowledge, all this building of knowledge and building of theories tells you that the Big Bang had a certain moment in time beginning, and all the matter that exists in the universe now comes from a very small point, from where everything expanded in a way, to give an image. But to have this finite, tiny point with this enormous amount of energy and matter density, you must have a way to put all together, and the only conceivable way you can see about this is a symmetric way of thinking, that you must have the same amount of matter and antimatter. And then, of course, you can ask yourself, so why there is not myself in antimatter that is destroying me? So in a way, there is a tiny difference between the matter and the antimatter that makes all this exist. And this is certainly a mystery. There are other mysteries, like the amount of dark matter. We see that if we look, we can look at this kind of phenomena also in the space. And we can look at the matter in the space, and we cannot really compute totally the matter that is in the space. We can compute it, but we see that there is a deficit, and there is what we call the dark matter and the dark energy, that are not exactly the same thing. To make this size of the universe and this way the matter is distributed possible. And this is certainly a mystery. Another mystery I would like to give you is that I explained to you that the energy and the time, they are correlated, and the product of the energy and the time has to give you a constant. Now, if you think for a moment that the time that you aim at is 0, then to keep this as a constant, the energy has to be infinite. So there is into this itself a paradox, and there is something that maybe we cannot approach. We can do our best, but the time 0 is something that is difficult.
So what we do in the research sounds a bit strange. I mean, in one hand, we want to make a confirmation or test of our present theory, and at the same time, we are always looking for something which asks destroying our present theory to go to something to find something new. You would like to have the explanation of this Higgs particle? Yeah, this is yes. I mean the Higgs mechanism. I have been. This is one of my I have been wondering how one can explain correctly and easily the role of Higgs field and Higgs mechanism and Higgs particle. And this is something which is difficult for me to do. How to explain is, Higgs boson does such a special, very unique, important role, even, allowing us to exist. This such an important particle has never been discovered until 1 year ago. So this is a kind of very, frustrating situation. We know that theory works very well. However, one of the key element of the theory wasn't confirmed by experiment. Nobody has seen this exist or not. And now we have very likely be discovered. This has very likely be discovered. So in a sense, this has the last piece of our theory has been found and put into the jigsaw puzzle. But this is, if it is jigsaw puzzle, then it is a completion, and you may just glue and put on the wall, or you may want to disassemble and start. But this in physics, this is doesn't go like this. Up to the analogy of last piece of jigsaw puzzle works fine, but as soon as after that, the analogy doesn't hold anymore. So what we want to do is, first of all, we have to still confirm if this particle is really the last piece of this jigsaw puzzle, not something similar, but some which may be totally different.
Oui, surtout que vous ne mettez pas une configuration maybe there is a presence because of the
No, there was 3 options, I remember. Tumba and fire.
we have a picture, which is a cosmological history of our universe. Nobody tells us that is the truth, but within our present knowledge, this is the best we can do, and indeed, it does explain very nicely all what we are able to observe. Now, maybe we will come up with new observation. Remember, there is fundamentally in the universe, what we are studying at LHC, I thought, is matter. So matter constitutes only, well, the visible matter constitutes only 4% of the universe. All the rest is unknown, being dark matter, which is something we know it exists, but we have no clue on what it is. And even something even more mysterious is dark energy. So, which is something we suspect it exists because we need it to explain given properties of the evolution of the universe. But again, we have no clue what it exists. So in other words, today we are in a situation we have a poor knowledge of 4% of the universe, and we ignore totally what the rest of the universe is. So the specific place where we are now, this is Alice experiment. We are looking for recreating primordial matter. This is the matter as it existed shortly after the Big Bang. And here we are talking about a fraction of microseconds after the beginning of the universe. At that time, temperature were extremely high, energy density was very high, and matter was in a completely different shape as it is today. So we recreate this primordial state of matter and try to understand what are the nature and the properties of this primordial matter, and then how it evolves from its state in the early universe to the state as we know it today. Just imagine, in a single collision of two lead nuclei, we are producing about 10,000 of particles which are going through our equipment. And all these particles, we have to look at it, to see it, and to identify it. So, of course, we don't take a picture of the particle itself. We take a picture of the track a particle leaves when it goes through our equipment. So it's more or less the same as if you would go on a ski slope. You don't see the skier, you just see the traces of the skier. And out of the traces, you say, okay, here was a skier, he went from there to there. Looking at the depths of the trace, I can have an idea on the weight of the skier, and we are doing the same exercise. We never see the skier, we just see the traces. And of course, to have a full trace of a skier, you need a big field. We are really using brute force. We are not very smart. So we use the energy we are able to make, to create in a collision, to create these new particles. Now, of course, this is for the creation part. So you need to bring a small particle to a very high speed. When I'm talking about high speed, is something which is very close to the speed of light. So for that, you just need a big machinery. The machinery being, well, you need magnet to make a particle turn, and you need electric field to accelerate it. And then 1 million of different elements just to make the whole thing work. I think CERN is, for me, really the best example in the world for humanity following a common objective. And this is, if we don't discover anything in science, I think having achieved that is a major achievement.
CCC recognized that it was a crash button. We're speaking about this new crash button which were installed like a year ago in each rack, or not?
I don't know.
No, basically, this I think we have to understand.
I think we have to really understand
was somehow recognized to be pushed, and bring this to the technical coordination.
I think Christophe Schopper also has to be involved in this.
So that's the suspicion right now, is that someone hit the crash button?
No.
So that's the question. So why did it turn off in the first place?
All the information it receives emergency stop there.
It received emergency. So it's as if someone hit the crash button.
So,
I mean, Craig, what's the meaning of emergency stop? I don't know. It's not.
No,
so
that's okay.
this
That's
is
okay.
Christophe Schopper.
So the log is as if it's as if someone hit the crash button. We don't think someone did, but it's as if someone hit the crash button.
Okay. So the question is about the first statement in the slide, that you looked at reprocess versus prompt data, and you decided to stay with the prompt, but in the reprocess data there are largest changes for jets, so I find the statement a little bit surprising.
So the question is there a quantitative measure of this no major differences which you see? Do you have some plots or so that show that? If it's in the backup, we can look at it later, but I don't want to kill the stream.
I'm not sure if I put it in the backup or not.
Just more than a sentence, I think that's what I learned from the question. But okay, we can take it offline and we can go on from here. You look frozen. Are you still, alive? I think the shock was too much on this question. He's gone. Okay, he became invisible. So no more questions till the end, please. Can anybody outside CERN still hear us? This could also be us. Oh, good.
I can hear you.
So I can go and sit down and just wait.
At the beginning, I was heavily involved in building a system that we call the trigger system. And this trigger system actually selects online in real time only the interesting collisions that will be recorded and that will be analyzed later. Now, this involved the development of an electronic system which operates very, very fast. It looks at the collision 40 million times per second. It is sort of a digital camera which takes 40 million pictures per second. It analyzes, it doesn't take these pictures, but it looks at these pictures and looks if there are some interesting patterns, for example. And if there are interesting patterns, which is the case only maybe a few hundred times per second, then this trigger system recognizes these and marks these photographs, if you like, really for recording. So we do not, like when you take photographs with a digital camera, you take many snapshots, but you eliminate those that you do not like. But we do this online extremely fast. Our first important discovery was a particle that looks very much like the so-called Higgs particle, which is also called God particle, but this is a term that physicists don't really like. So anyway, we have discovered a very new particle, and now we are going to measure all its properties and to make sure it is really the long-sought Higgs particle, or if it is indeed something completely new. But actually, this experiment was built for another main purpose, and this main purpose was really to discover if there are, for example, new forces in physics. We all know gravity, for example, but there are also other forces, for example, electromagnetic forces in the universe. But maybe there are even other forces we do not know about, and this could be discovered at this experiment here. We could also, for example, discover completely new spatial dimensions, which may be very small, so that up to now we have not been able to see them. But with a tool like the Large Hadron Collider in this experiment, we can use this really just like a giant microscope, so we can really look deep into nature, and we hope to find something very new. For example, it is imaginable that gravity becomes a very, very strong force, much stronger than we are used to it, when we go to very small distances. For example, when you smash two protons against each other, as it is done in the LHC, then you really come to very, very small distances, and it is possible that gravity becomes very strong. So if gravity becomes strong, then we could also create mini black holes, microscopic black holes. So this would be a spectacular new signature for up to now unknown physics. It's a constant struggle, and of course the kids sometimes complain, "Mommy, there's nothing to eat, what shall we eat?" But well, I'm not alone, and one has to get all the help one can. And but I think even if the family suffers, I think in the end they see how enthusiastic we are, and they see that we really have achieved something that is really satisfying, that can show new ways, and I think normally families understand. But I should also say, I mean, there have also been lots of divorces at CERN here, and mainly because of just too much work. But people are enthusiastic, you know. I mean, these are not people that come at 9 and they leave at 5 and they look at their watch, you know. They really like to spend the time here, and they put in all the means they have to bring out results, and to also to get personal satisfaction.
This center is at CERN and has essentially two main, very important connections. One connection brings us to the experiments. So essentially, the main flux of data is from the experiments to here. So when there is beams are colliding, the events, so the collisions, the result of the collision are recorded, filtered across different levels of filtering, and eventually they are shipped to here via a dedicated network. So this is the first connection. The data arriving here then are stored on disk immediately, and they are ready to be immediately analyzed. This is just the first part of the analysis. Actually, we call it general reconstruction. And the idea here is that out of the raw data, this is also the technical term, the raw data which we are receiving from the experiments, we reconstruct trajectories, for example, from which you can identify particles and give to them, let's say, assign them energies and directions. These data are also shipped outside, and they are shipped initially, I mean, directly from CERN to a set of important computer centers, more or less comparable to this one, which are then, in turn, redistributing the data to other places where, I mean, typical university or university type of facilities, where the final analysis, for example, will be done, or other activities connected with the analysis of the data. So I think one can visualize data coming from the experiments, being stored, being given to this initial reconstruction, and also being distributed. So this is, let's say, the backbone of our activity. I was born in 1964, and I think, talking with, let's say, people of my age, etc., I came to the conclusion that, the Apollo period, end of the 60s, beginning of the 70s, had really an influence on us. Initially, I was very passionate about astronomy and astronauts, this kind of, which eventually, when growing older, became an interest in physics, and so then I decided for. But I think there is a very specific, interest correlation with astronomy and with that particular period of space exploration. On one side, astronomy is this gigantic, these distances, worlds you cannot really visit directly because of distances. And once you go for particle physics, is a kind of, mirror image of this. You go in the smaller and the smaller and the smaller. So you find there are worlds which are really fascinating, strange sometimes, bizarre, but it clearly is. This is one of the things which clearly moves me, or moved me to go in physics. And now, even if I'm in computing, I'm more on this side, clearly there is the proudness to say, well, these experiments are doing really something really interesting, really cool, and we are giving our small contribution to this. So it's I think for somebody with a physics background, CERN, even if then you move, keeps this fascination. I mean, it's our home. It's our dream place. So it's I think is this.
We have our own fire brigade. We have our own emergency services. Actually, we are like a city. And this is a challenge also for my job, because you asked me in the beginning where we are here. We have to manage a small city. And just to give you some ideas about what I mean by city, we have roughly 10,800 guest scientists coming from all over the world, 120 nationalities. We have roughly 2,500 staff. We have 500 postdocs, 500 students and apprentices. So it's a population which needs accommodation and services as any customer or client would have needed it in a small city. Actually, in some sense, we are at the same time an organization like any other organization, but we are also providing our own legislation, if you like, because the convention gives us the right, but also the obligation to handle certain things ourselves. For example, if we fix our salaries, we cannot do it just like that. We have to do it according to the rules which were approved by our 20 member states. So in some sense, we are kind of a state in the states. What you need is a long breath. And this is sometimes a problem if you discuss things with politicians. They're used to work with horizons of 3 to 5 years. And they expect a return on investment which is more or less immediate. Immediate means tomorrow. But we have seen, if I take the example of the World Wide Web, which was invented here at CERN, you need sometimes, I would say, on an average, at least 10 years, 10 to 15 years, between the first basic ideas and the first industrial product.
So I'm a theoretical physicist, so my job, is to come up with some ideas, some possible explanation, and then I'm trying to understand what are the consequences of these ideas and how you can test those ideas using experimental results. In particular, the experimental results that are obtained now in this LHC, this big machine that have been built here at CERN and is working pretty well at the moment. I mean, some good ideas can come up at every moment, and you have to be ready. Right? And it can be dangerous, in particular when you are driving your car, right? You should try to keep your ideas alert and be prepared when you are getting back home to take a little piece of paper, write it down your ideas, and try to finish your computation. Most of the time you are stupid, you are making errors, etc. But from time to time you are right, and you understand exactly something new. And that's fantastic, of course, these days. When you are coming back home in the evening, you are feeling very good, right? Because you are feeling very good because you are more knowledgeable in the evenings than in the morning. And the feeling that you understand that something that nobody in the world had thought about before, right? That's really what is exciting about research. For a few hours, for a few moments, you'll be the only people on the earth to really have a clear understanding of a problem. Discovering the Higgs boson is not like discovering yet another particle. What we are really after is really trying to understand some fundamental laws, some fundamental principles that govern the universe. So for a very long time, one main theme of particle physics and theoretical physics, high energy physics, was the gauge principle. So the gauge principle is really the theory that explains how particles interact with each other by the exchange of the gauge boson. And maybe with the discovery of the Higgs boson, we are about to discover a new fundamental principle of nature that could really govern how the universe is structured. But again, we are not so much interested in new particles. What we really want to understand is what is the principle behind these new particles. Is this discovery of the new particle is telling me something more fundamental about nature? More fundamental, for instance, could be, is there a new space-time dimension? Is there new interactions, new fundamental interaction between those particles? That's really what we are about, right? The fact that, up to now we understand interaction as the exchange of gauge boson. That was a really big step forward in the understanding of nature. But still, there is few things that we don't quite understand. For instance, the fact that electromagnetism is described by one particular symmetry of nature. There is a weak interaction which is described by another symmetry. There is a strong interaction, yet another symmetry. Why those particular symmetry? Is there something deeper behind those symmetries? A bigger symmetry, for instance, that will unify all those symmetries associated to the different interactions? And we're trying to understand these kind of things. We have good ideas, but we still don't know if our ideas are true or not.
ça tient. Il est pas bien centré là. Je vais juste appeler Gilles, parce que j'avais dit que je l'appelais. Ouais, bah, fais encore un ou deux couples, elle va te casse pas la tête. Tu descends? Ouais,
I mean, I'm not a physicist, and I used to explain that I'm here to develop the toys for physicists. So I'm involved in the machine side. So there is several people at CERN deciding what has to be done for the physics, and then we are in charge to develop the tools in order to allow these people to make the research. There is not really hierarchy at CERN, or at least this is my feeling. There is people from the physics side deciding more or less what has to be done, and we are here to provide them the required tools to be able to investigate what they are looking for. So there is no real hierarchy. There is there is different specialities at CERN, and in the technical part. So our section is called MDT. My actual section leader used to translate that by making dreams true. So there is people asking for some dedicated tools, and we are here to try to develop these tools. So we are presently working on a new generation of superconducting magnets using a new technology, niobium-3 superconducting cables, in order to reach higher field that will be required for the upgrade of the luminosity of LHC. So the magnets presently installed in LHC are based on niobium titanium technology, and we reach the limit of the magnetic field that can be reached with such a kind of superconductor. We are trying to develop a new niobium-3 dipole, 100 millimeters bore with 13 Tesla. And to give you a rough idea about what this represents, the required niobium-3 cable to produce one coil is around 100,000 Swiss francs per coil, and we need 4 coils inside. And you just need a few seconds to destroy the cable, so this is quite difficult to deal with.
We are working in superconductivity, so the magnets we have to test, they have to be cooled down to a very low temperature. In this case to 4.2 Kelvin or even to lower temperature, which is 1.9 Kelvin. Now, to do that, you need a kind of a thermos, what you need, a vessel that is well insulated from the outside, which is very warm with respect to the magnet. Basically, you have a 300 Kelvin difference, which would be the same if I say 300 degree, because it's a relative number. So then you have to make possible that the heat in leak is really minimum. So we build equipments which are essentially made by a vessel itself, in which we can put the magnet. Then we can, obviously, we close it, and we can access it by a liquid, which is in this case liquid helium, and to cool down to 4.2 K. And then to this equipment we have to connect the powering, because obviously the power generation is on surface and in a nominal 20 degrees Celsius temperature is in the hole. So you have to bring the current into the magnet through this vessel. So this vessel is also helps us to make the interface between the magnet and the outside. And then obviously we have all the information coming out, which are in form of wires, and we are plugging into cards for data acquisition. And then we have behind a control room where on front of us through computers we get the information visible and in the graphical way, such a way that we can analyze them later on. So that is essentially what I have behind, and basically you have here behind me 3 test stations of this type. So 3 units which are nearly independent one from the others. Well, my family is completely here, because I have to say my husband is working at CERN. My husband is working in the same area that I am doing, so he's doing also magnets. And okay, life is like this. We have a 3-year-old child, and she's going to the school, kindergarten at CERN. So in the morning we are coming in family at CERN, and we are dispatched all over the 3 sites. My husband is working in the Prevesen side, which is in the French area. I am working between the Swiss part and the French part, still in French territory. And my daughter is on the Swiss side in the kindergarten. Yeah. My husband has also another son, by the way, he's in the control room. So I have his family also. I have my brother-in-law working in Atlas detector. So at the end, yeah, we are all a family. We are here, yeah. Well, when you are saying that we have to leave maybe some space for imagination, you are assuming that what we are doing is enough to understand the world, how the universe works. I'm not so sure. I think that we are in a territory where we are so difficult, and somehow so close to understand what is the complete stuff, that it becomes very, very hard to improve. And I am not at all convinced that these steps, which are big itself, are big enough to get rid of the space which remains there. So I think that we are on the top, but this is going very slowly, high and high, but I think that we are still very far away. I'm not sure that it will come next year. Higgs, we explain Higgs, and then the dreams are gone. No, I think that going ahead, we will find the new elements which may bring, that is my idea, of course, probably will bring us closer and closer, but I'm not convinced that we will understand the complete picture.
you might know there is a principle which is called the anthropic principle, and say the whole nature, laws of nature, has been designed only to make it possible that man can exist. But I doubt it. Of course, we also realize that science, physics, is only one perspective of understanding reality in nature. And I had a long discussion here with the Pope when he visited CERN, not the present Pope, not the previous Pope, it was John Paul II who visited CERN. So I discussed with him, can there be a conflict between science, between physics and religion? And he agreed, no, cannot be a conflict. He agreed to that. And then I asked him, well, if you agree, why don't you rehabilitate Galileo? And I said, look, if you have a plate, an eating plate, you're looking at it from top, you would say that's a circle. If you look at it from the side, you say that's not a circle, that's a line. So this will be two conflicting perspectives. And we might ask forever, is it a line or is it a circle? So that's what religion and science does with reality. We're looking at reality in different projections, and we see one projection, religion sees another projection, and we might fight who is right. In the end, these are two different projections of the same reality. It takes a long time to clarify a certain concept. How do we define something? So the real imaginative thing in natural science is to create the concepts which are necessary to find the laws of nature. And maybe these concepts are not unique. There might be a different way how to describe nature by different concepts.